Right. Welcome back, everybody. So we're happy to have Elijah Bodish, who will tell us about diagrammatic projectors for Lie algebras.
Yeah, thank you for the introduction, Josh. Thanks for inviting me and for listening. So this is going to be a talk basically where by the end I'll just report on some project that I had a couple years ago, as well as a project that's joint with Han Wu, who's a graduate student at UC Davis. So the motivation, sort of the historical motivation maybe for a bit of this problem is that if you have a semi-simple Lie algebra over the complex numbers, you can obtain from this two different things. So on one hand, you have a root system with a set of simple roots inside of it. And on the other hand, you have the enveloping algebra, which you can use to study the representation theory of your semi-simple Lie algebra. And there's a theorem of Sayre that gives a generators and relations presentation of the enveloping algebra, which basically is built out of just the combinatorial data of the root system. So you have some generators determined by the simple roots, and then all of the relations are kind of, there's some structure constants and they're completely determined by this root system. So just quick reminder of some examples. So if you have SL2, here's your root system, generators, F, H, and E, and then here's some relations. And you can see that the structure constants appearing, this 2 is determined by this root system. So there's some pairing on the root system, some other data, but it's all encoded in this combinatorial gadget that you obtain from the semi-simple Lie algebra. Another example, SP4, there's some other numbers that you're obtaining from your root system, and these give you some structure constants in the algebra. So again, just more background, probably everybody's familiar with it, but it's nice to still point out what's nice about this theorem. So one thing is there's the question of existence. So there's a theorem that you learn in graduate school that says that there's a bijection between semi-simple Lie algebras, or just simple Lie algebras, and irreducible root systems is an easier way to say it. And the fact that there is this bijection, one of the ways of seeing it is that you utilize Sayre's theorem. So it actually tells you that there's such a G for every possible root system. And previously, historically, you might have had to sort of case by case proven that such a Lie algebra exists. So in the case of G2, you would look at the automorphisms of the octonions, and you'd have to know that the octonions exist to even see that G2 exists. But here, this presentation of the enveloping algebra just gives you the existence of G2 based off of knowing the existence of the root system for G2. And then it got kind of even, that was maybe why Sayre proved his theorem. It was just in a textbook or in some lecture notes originally for this existence purpose. But then later it got interesting because in the 80s or 70s, I guess, for the affine Lie algebras, there was work on sort of giving extensions of semi-simple Lie algebras to quantum groups or Cas-Moody groups. And this is built off of the Sayre's theorem. So this presentation, you can generalize it based off of a more complicated root system, or sort of deform the presentation, and you get these new, more interesting algebras. And then, of course, why do you all like presentations of associative algebras by generators and relations? Well, you can construct representations just by giving some linear operators on a vector space satisfying those relations. So you can construct explicitly some presentations of the Lie algebra because you just know that it's given by generators and relations. So that's this important but still classical problem. And maybe a slightly more modern problem is to think that you have this Lie algebra G, and instead of obtaining the enveloping algebra of it, which is an associative algebra, you can obtain a monoidal category. So G gives rise to this monoidal category rep G, which maybe is bad notation, but just this will for us mean only finite dimensional G modules. So rep G is just the monoidal category of finite dimensional representations of this semi-simple Lie algebra. And the modern problem, or I mean, a problem, is to find a generators and relations presentation of rep G. So what that means is you want to sort of find some universal property that allows you to construct actions of this monoidal category analogous to how you would have constructed using the presentation of an associative algebra representations of the associative algebra. So in the case of presenting an associative algebra, the first step is just you want to have some elements which you think will generate this algebra as an algebra. So in the case of presenting this monoidal category by generators and relations, the first step is to get some generators. And because it's a category, we're going to need generating objects and generating morphisms. So it's a monoidal category, and that means that generating objects as well as morphisms can be chosen to be things that generate monoidally. So there's composition of functions, which is like the multiplication in an algebra. And there's also tensor product. And this tensor product allows us to have a smaller set of generators than maybe you would initially expect, or maybe historically you might have expected. So a seemingly natural choice, although still somewhat arbitrary, is you could choose, well, for G, you have these fundamental weights. There's one for each simple root, and they're dominant weights. So there's an associated irreducible representation of G with highest weight, that fundamental weight. And such a representation will refer to as like a fundamental representation. So an irreducible representation with highest weight, a fundamental weight, that's going to be a fundamental representation. And notation, just like I wrote rep G for the full monoidal category of finite dimensional representations, I'll write fund G for inside of this category of all representations, there's a full subcategory where the objects are just tensor products of fundamental representations. So I don't allow all representations, I just take tensor products of these various irreducible representations with highest weight of fundamental weight. So what's nice about this choice of generators, so the generators are being just the fundamental representations, since I'm generating as a monoidal category, I can tensor product them together, and those will be in my sort of generating set because I'm generating monoidally. So if I have any dominant integral weight, I can just decompose it into fundamental weights. And then I use that decomposition. Using that decomposition, I can see that there's a way to view my representation with highest weight, that arbitrary dominant integral weight, as a direct summand of some tensor product of fundamental representations. So I have all of these fundamental representations that I'm generating with, and it really does generate in the sense that you would kind of want it to, as you're generating your category by these objects, and that every object, every irreducible at least, is a direct summand of a tensor product of these fundamental representations. And because I'm working in a semi-simple category, if every irreducible object is a summand of a tensor product, every object is a summand of a tensor product. So this V of lambda is going to be sitting inside as a direct summand some object in my category fund G. One of the weird things about the category fund G, though, is that it's a little bit different than the usual categories you might think about in representation theory. It's not an additive category. You can't take a direct sum of two things, and you can't take the image of an idempotent or the kernel of a homomorphism in this category. The objects are just tensor products of fundamental representations. But there's a formal process known as the Kurubi envelope, where you just take the objects in this category, which is the Kurubi completion or the Kurubi envelope of this fund G, to be, well, you allow yourself to take direct sums of objects, and then you also allow yourself to take images of idempotents. And then semi-simplicity tells you that actually that category will be the same as the full representation category. So this is some universal property itself. And our goal was to give a generators and relations presentation of the monoidal category of all representations, meaning we want some universal property, some way to get rep G to act on something. And because of the universality of this Kurubi envelope construction, we can really just focus on this fund G. So if we can describe fund G by generators and relations, by general abstract nonsense, we have described rep G by generators and relations. So formally, that makes sense. I mean, it's okay, but in practice, what does that actually mean? Well, we have this category where we don't have images of idempotents, and we want to build our category that we're interested in by taking images of idempotents. So the first step, I guess, is to understand what are the idempotents. Let's see. So this is just a little comment. I mean, a reminder that generating objects, because that's what I'm looking for, tensor products of fundamental representations. And then on the other hand, I'm pointing out why study this fund G. So historically, this is just something that people ended up studying as a generating subcategory in this problem of describing rep G by generators and relations. You don't have to choose it. For example, if you're looking at, I mean, for other categories, there sort of are other choices of representations that appear maybe more naturally. Like if you're a linear group, you have the natural vector representation. You can take tensor products of that and build some new category that's like fund G, but might seem easier, like the Brouwer category or something like that. But what I like about fund G, at least is sort of how I'm trying to sell it right now, is it seems to be type independent. You don't have to say something like natural representation, which maybe E6 doesn't have. And I'm hoping to convince you that this is a somewhat natural choice from that perspective. So just an example of how this how this category fund G might look. So for example, if your Lie algebra is SL2, here's your root system. Your fundamental weight is just 1/2 of that simple root. And the fundamental representation in this case just is the vector representation. So there's only one fundamental representation, it's the vector representation. And the category fund G in this case, when you're just looking at SL2, is exactly tensor products of that vector representation. So objects are just going to be tensor products of this vector representation. Morphisms are going to be all maps between these tensor products. So there's some basic things you can do with these vector representations. Well, it carries a form, and you can use that form to identify it with its dual, and that gives you some maps from the double tensor product of this representation with itself to the trivial module, and from the trivial module back. So you just do some linear algebra to get some SL2 equivariant maps on these double tensor products, and you can write down, I sort of give you explicitly what these maps do on a basis. So these are some maps between fundamental representations. So one thing that this is useful for pointing out is that, just to have in the back of your mind, this category fund G that I defined, this objects are tensor products of fundamental representations. We allow the empty tensor product, and that's the trivial module. So the trivial module is appearing in this story as well. So it is really a monoidal category. Monoidal categories have to have monoidal units. So the theorem then is that these actually are generating morphisms. So you have these two maps, and you can then generate a monoidal category. So my notation, which is just what I'm using in this talk, is going to be that I have this right-hand side, which is going to be a presentation as a monoidal category. So as a monoidal category, I need generating objects. So I can just think of the generating object being some abstract picture of a single dot, and I'm allowed to take tensor products. So if I tensor product this object with itself, I would have two objects next to each other. Three objects next to each other would be a triple tensor product. It's a strict category, so there's no issue to take care of whether I'm associating my tensor product one way or the other. I'm just saying that all these tensor products will be the same thing, which is just n dots. And then I have some generating morphisms, which will be, so up here I drew the morphism, I gave it the name cap and the name cup, but I can abstractly just view these maps as being a map from the product of two dots to the trivial representation, which is the empty picture, and I just draw it as a cap. I also can draw this as a cup, and I get a map from the empty picture to tensor product of two dots. And then there's some relations. So you can just check that because of the linear algebra here, I have this relation that if I sort of snake one way, I can pull it straight. And if I snake another way, I can pull it straight. And then I also have the dimension of the vector space is 2. And so if I compute the value of this circle, I have an endomorphism of the trivial module, which must be some scalar multiple of the identity. And I just get the number -2. So I get the dimension with a sign coming from the fact that this is a symplectic form. So I have an abstract generators and relations monoidal category on the right-hand side. And the theorem is that this is actually the same or is equivalent to the category of fundamental representations, meaning on the one hand, all maps between tensor products of C2 tensor D and C2 tensor E, if I have any map, I can realize it as a linear combination of a composition in the monoidal sense and in the function composition sense of these generating maps. And then also, the only relations I need to impose are these relations here, these few simple relations.
Can I ask a question real quick?
Yes.
I'm trying to fixate on this fact that you don't get to take sums of representations.
Yes.
And so the point is that I'm taking tensor products. I can have mixed tensor products of representations, or am I only taking default tensor products of the same representation?
So
And,
right.
And so I'm trying to think about these projection operators as like they would be projecting onto something different in the middle. So I'm a little bit worried about that. But yes, I'll leave it there.
Okay, right. So I'm definitely will hopefully I'll be able to make sense of that. But yeah, the idea is that I've got my objects are in this category fungi are just exactly the tensor products of fundamental representations. So you're right that if I have a map from here to here, I'm not allowed to factor through anything except for another C2 tensor something else. So in terms of the actual definition of this category, all my maps are only factoring through these objects. But in the Kurubi envelope construction, when you adjoin an idempotent, the idempotent becomes an object. An object is, I guess I'll just write it here since you're asking. So if I have a category C, an object in the Kurubi envelope will be a pair X, where X is an object in C, and E, where E is a map from X to X, such that E squared equals E. And this doesn't refer to any, the image of the idempotent corresponds to this object in the other category, but you don't have to actually have that object in the other category in your original category to see it. Hopefully when I say a little bit more, it'll become clear what we're up against in terms of constructing these projectors. But yeah, for now, I just wanted to maybe more simply like explain what I might mean by a presentation of a monoidal category. Okay, great. Any other questions? Okay, so quick remarks. This presentation does describe a recipe to get actions of this category rep SL2. So I have again hidden in this Kurubi completion, but it's true then that monoidal functors from rep SL2 to endomorphisms of some category is just the same as I choose a single endomorphism of my category, some functor from my category to itself. This should read C over here. And then I need it to be self by adjoint, and I need the unit and the co-unit to satisfy this -2 relation. So that presentation on the bottom right hand, or you can see it down here as well, that's describing this universal property, but for monoidal categories, which is completely analogous to the associative algebra story. But instead of acting on vector spaces, you're acting on other categories. The other thing to say for maybe more experts is that this presentation, it's not just for rep SL2, it's generalizes to quantum groups. And in fact, more so, it generalizes to quantum groups at a root of unity. And in that case, this Kurubi envelope is not all representations. When you specialize to a root of unity, you get, as the Kurubi envelope, an additive category that isn't an abelian category. It's the category of tilting modules. You have direct sums, and if you tensor product things together, you can decompose it into direct sums, but you don't have kernels of homomorphisms.
Sorry,
so that
this tilting category, is this for the small quantum group or the BLM?
This is for the usual quantum group, but it's but you make sense for it. So it's for the Lustig form, I guess.
Okay.
Is which the category then probably should be the same as the BLM one.
Okay.
Yeah, but it's not. It somehow is not a small quantum group thing. There is some paper that at least is a preprint, which is some generalization of the Temperly-Lieb category to the small quantum group. But I think it's still kind of work in progress to actually finish that project. And that's not a project of mine. I can't remember the authors, but this is something that people have thought about, and it's a little bit more complicated.
And so this tilting category has infinitely many objects?
It actually has infinitely many objects. So there's other tilting. So the reason I'm mentioning here is that I just want to kind of remark throughout on a few other related things. But yeah, but the tilting category that's like the quotient of this one will certainly appear later.
Okay.
So yes, so this is okay. Now I can actually address this business about idempotents and what's going on. So how do we understand V of n via generators and relations? Well, in my category, this is like a picture of maps in rep SL2. So the usual thing that we're used to working with is just the actual entire category of all representations. So I have my vector representation C2, as I was calling on the other page, and I can tensor product with itself any number of times. It is a tensor product of fundamental representations, so it's in this combinatorial category fund SL2, but it's also a representation of SL2, so it's in rep SL2. And then I have this other object V of n, which is now some arbitrary irreducible representation of SL2, not in the category fund SL2, but it is a representation of SL2. And I have this usual setup. I mean, there's going to be a projection to V of n from V tensor n, and an inclusion from V of n into V tensor n. And I can insist that the composition of inclusion then projection is just the identity on V of n. And if I insist that, then composing in the other direction, if I project and then include, this composition is here. So I go from V tensor n to V tensor n. So that map is a map between tensor products of fundamental representations. It's an idempotent with image, this highest weight irreducible of highest weight n. But it's a homomorphism between fundamental representations. So this theorem of Temperley-Lieb tells me that I can express it as a linear combination of diagrams. And my notation is that I'm just going to kind of write n in an oval. This is going to be a map from V tensor n to V tensor n, which is this idempotent. But I'm thinking of it in the diagrammatic category, which is just going to be some linear combination of pictures. So I want to understand some of the combinatorics of this linear combination of pictures that's describing the projection to V of n. And this was studied, and it's the origin for all the rest of the things that I'll say. And so this is a theorem that is due to Jones, I guess, separately from Wenzl, but these are going to be what people in the literature call Jones-Wenzl projectors. So these are elements in the Temperley-Lieb algebra, but we're viewing them in the Temperley-Lieb category. And it tells me that I can understand this idempotent here in terms of another idempotent and then some strand. So this is like a simpler picture on the left-hand side, and then something built out of cups and caps, and then weaving together these other previous idempotents. So this is also something simpler. And because this, I mean, I'm allowed to take linear combinations of maps, so I could simply subtract this thing over to the left-hand side, and this would give me an expression for this idempotent. So I have some recursive relation describing my idempotent in terms of previous idempotents and some of my generating morphisms in my category.
Sorry, Elijah. In the second sum, that n-1 idempotent, I mean, is there a reason why you write it there? I mean, it gets absorbed, right?
I agree. Yeah. So it does get absorbed, but the reason I write it there is that in B2 or G2 or SLN, it doesn't get absorbed. Okay. But it is still there. Okay. So this is just a philosophical point that it's like, I mean, this wasn't my observation. It was my advisor's observation. So I think if you keep track of this thing in the middle, it ends up being helpful psychologically.
Okay.
But yeah, this is a great point. Like experts always get rid of this part in the middle for SL2, but I think it'll be important later. So let me just remind you, this is probably kind of boring, but I'll just like quickly go through how these guys, how Jones and Wenzl sort of proved it. So you have a decomposition in your category rep SL2, which is I take v of n and I tensor it with v of 1. So this is the usual formula for tensoring with a funda, the vector representation for SL2, the Clebsch-Gordon rule or whatever. And I get v of n tensor v of 1 is v of n plus 1, direct sum v of n minus 1. And in diagrams, that means that I can take the projection to v of n and tensor it with the identity of v of 1. And this isomorphism, it has to be realized by the identity is a sum of two idempotents with image v of 1 with image v of n plus 1. Well, my formulation is just that I get to call that n plus 1. And the other has image v of n minus 1. So that's going to be some idempotent with image v of n minus 1. Now, this diagram that I have is a quasi-idempotent with image v of n minus 1. So that's like kind of why I'm writing the n minus 1 here. So it has image v of n minus 1. You can see it in the middle there. It's factoring through that. And it's quasi-idempotent because, well, probably nobody can read this, but there's some calculation that you do where you square it with itself. And by doing that, you mean you take this thing and stack it on top of itself in the vertical direction. And then because this term in the middle is an idempotent, I can replace two of them with a single one. And then this middle diagram, my idempotent with a little curl on it, that's an endomorphism of this irreducible representation here because I have an idempotent there. So by Schur's lemma, I can just pull out some unknown scalar and then reassociate and I get the diagram back. So this is definitely a quasi-idempotent. And to finish Jones and Wenzl's story, you just need to figure out what this scalar is. Now, to do that, this is kind of where the fun comes in. You can take your calculation and do it maybe backwards or inside out or upside down. Not sure the right exactly way to phrase it, but here I have the thing that I want to compute on the left-hand side. This will be equal to some scalar multiple of the identity. And on the right-hand side, I can just use inductively my formula for this idempotent. So remember, I'm trying to write a formula for the n plus first idempotent. I want then to use this formula for the previous idempotent. And I can plug in my recursive formula here. And then simplifying these diagrams on the right-hand side, using the relations in the category as well as the various orthogonality and absorption properties of my idempotents, I get this recursive formula. So I get kappa n, which is the coefficient I'm trying to compute here, is equal to, well, the circle is -2. And then I have this -1 over kappa n minus 1. So my initial condition is that k1 is equal to -2. And that just tells me that k sub n is minus n plus 1 over n. I can solve that recursion. So it's just an exercise to check that given this initial condition in this recursive relation, n plus 1 over n up to a sign uniquely solves it. And that's it. So you sort of start with a theorem that says I have a diagrammatic description of my category. And that tells me that I can abstractly write my idempotents as a linear combination of these diagrams. And then you use something about the tensor product decompositions in your category to tell you that abstractly, I know the form of my recursive relation for my idempotent has to have some shape like this here. And then from that, you have some obvious candidate maps, which are these quasi-idempotents. Those will be like this, and this quasi-idempotent, the only thing you need to do to figure out what Jones and Wenzl's formula is compute the scalar that you get when you square that quasi-idempotent. and then you can rescale by its reciprocal to get an honest idempotent. So most of the, maybe the most interesting step here is somehow this last part. Are there any questions about this review of how this goes? Okay, yeah, and then just remark for the experts. So let me say something. So applications of this formula, so it's been used, the formula for the Jones-Wenzl projector has been used in various places: circle bimodules, theory of subfactors and planar algebras, link homology. So it somehow is a useful thing to know. I mean, if you're interested in in fields that are just even adjacent to representation theory. And then, Josh was asking about these other categories that are related to roots of unity. So I'll just, gives me a reason to point this out. So you could also think about this negligible quotient of the category of tilting modules, which is the sort of finite piece of the category of representations at a root of unity that topologists like to think about. This is where you get these three manifold invariants. And this idea that I learned from Scott Morrison's thesis is that computing these idempotents is actually giving you an explicit generators and relations presentation for these negligible quotients of the category of tilting modules. So for just an example of how one of these things looks, so if I have this tilting module, or this projector to the irreducible of highest weight 2, I can express it this way. And I have the ability to specialize my category to a primitive 6th root of unity, for example, and that tells me that well, I mean, I can use this formula to compute the dimension of this irreducible representation, and at a 6th root of unity, it's actually 0. So this thing that topologists do is that they throw away the objects that have dimension 0. So there's a monoidal ideal in the category generated by the maps between objects of dimension 0. And in the quotient, I get rid of this thing. The denominator here gives me a scalar that just ends up being 1. And so I actually have this relation. The identity is the cup cap in the quotient category. And so the new sort of thing that you could say, which is Scott Morrison's observation, although I'm sure it probably goes back before then, is just where I read it, is that this category of tilting modules modulo the negligible ideal. So this is where this category with finitely many objects occurs. This is, I take my original presentation of the category, and then I throw in the relation that says that these projectors with dimension 0 are equal to 0, but I can reinterpret that as being some other relation like this. So this is now my new set of relations, and this is what I wrote. I might be wrong here. It might be slightly twisted to that, but it's some relative of Repc mod 2. Right? And you can try to play this game with other projectors and goof around and see what categories you might get. So this is actually kind of a cool observation. I haven't ever seen like an actual application of this idea of having a hands-on presentation of these categories using to like this actual 3-manifold invariant. But I feel like that would be a beautiful thing that probably someday somebody will do. There is the work of some work of Kurubi and Melvin along these lines, but not quite what I was thinking. Okay, so that was all sort of remark for experts. Here's the history of presentations of fund G. So we saw SL2. This is this Temperly-Lieb category. It actually goes back to Hermann Weyl even studying invariant theory. And fast forward to 1996, Kuperberg, I guess, was the one who came up with the idea of studying tensor products of fundamental representations and maps between them as a generators and relations monoidal category. So he has this paper where he gives the generators and relations descriptions of the monoidal category fund G when G is SL3, SP4, which is the same as SO5 and G2. So this is a really cool paper, and it introduces this question that we're kind of talking about today. His student Kim then gave a conjecture for SL4 in his thesis. There is some partial work for SO7 by Westbury. Scott Morrison in his thesis gave a conjecture for SLN, and then later proved this conjecture with Kaudis and Chemnitzer. And then pretty recently with Elias, Rose, and Tatham, there's been, we defined and proved that it's the right answer, a diagrammatic description of fund G for G is SP2N. So it's nice. There's still plenty of open stuff here. I mean, all of the SOs, even or odd, except for a few of the low rank ones, and then all of these exceptional groups, except for the one low rank one that Kuperberg handed out. So you want to understand these presentations. Basically, basically just trying to solve this problem that Kuperberg posed, which ended up being maybe way harder than anybody would have expected. So that there's plenty of open stuff here still. So here's an example of a more difficult presentation. This is from Kuperberg's rank 2 paper, if you have SP4. So there's two fundamental representations, the vector representation, and then the second fundamental representation is appearing in the exterior square of the vector representation, but because you're a symplectic group, there's this skew form around that you have to get rid of. So this is actually a 6-dimensional module, but if you quotient, you get a 5-dimensional module. So there's this category, which is just fund SP4 is just a category with a 4-dimensional module, a 5-dimensional module, and all the possible tensor products of them, including, of course, the empty tensor product, which is the monoidal identity. And it has a presentation here. You've got generators, this one and this one. Maybe this is corresponding to the first representation. This is corresponding to the second representation. There's some maps between them, cups and caps, like we had for SL2, and now some more complicated kind of multiplication maps. I mean, this is wedge 2, so you can see that there's going to be a map from V tensor V to it. And various relations. So it's already totally non-trivial that this is an equivalence of monoidal categories, and Kuperberg proves it with a bit of effort. But the question then is sort of, can we generalize Jones and Wenzl's description of these projectors to this new framework where I have a more complicated diagrammatic category? So Dong-Seok Kim, who was Kuperberg's student, he was the one who, I guess, Kuperberg kind of sicked on this and started computing some of these diagrammatic idempotents. And here he did basically almost everything you could possibly do for SL3 in his thesis. And then he also did a little bit, but a decent amount for SP4. So he found the idempotents which are like projecting onto the top symmetric power of either the vector representation or this other 5-dimensional representation. So in the language of fundamental weights, he computed the projector for V of M times just a single fundamental weight, not for these other ones. And here's his formula here. So it's really very similar. You have a recursive description of the idempotent in terms of some simpler idempotents and some generating morphisms. So he has crossings, but they're just code for some complicated linear combination of other generating diagrams. And then there's some coefficient which he solves for. And then there's Ben's work, Elias's work, which is for SLN webs. And so here he has a conjecture which is still a conjecture. It's just was verified for a few small rank cases for the general form of the projectors. So there's a similar kind of flavor to this projector. You can see that you've got the thing you're trying to solve for, and then some simpler things, and then he has some complicated but understandable code for what this map is supposed to be. I mean, this is just a simplified version of it because this is like an arbitrarily complicated diagram. This is for arbitrary SLN and arbitrary weight lambda. And then he has also a conjecture for what the coefficients will be. So this is still open, and I would think it would be great to have somebody think about what's actually underlying this conjecture. I mean, namely, like how to actually prove it. But it's the guiding framework for now what comes next. So my idea was just simply, I'll just generalize Kim's work on SP4 to arbitrary irreducibles V of A and B, so multiple combinations of these fundamental weights. And the guiding framework is to use this sort of style of description of the projectors that Elias gave for SLN, where you can see here, he keeps track of the middle projector, whereas Kim did not keep track of the middle projector. So somehow, because in SL2, you don't need the middle projector, you would think that you could maybe not need it for the other ones. And turns out you don't need it if you're doing these edge cases, which are a little bit more SL2-like. But if you want to do the general case, I think you need to keep track of the middle projector. And so my theorem, I mean, I don't know, whatever. Here's some formulas for what the projectors are for SP4. And then let me say next, because I especially want to highlight the work that I've done with Hai Han, who's Kuperberg's student now. He's a graduate student at UC Davis, and he helped me immensely by doing these calculations with me for G2. So these are the projectors for G2. Same story, basically. Many like little diagrams, many formulas, and many pages of calculations that Hai Han did to unravel what this is. So the idea of the proof, it's really more or less the same as the SL2 case. Maybe it's underselling it a little bit, but it's very similar. And the point is that instead of in SL2, you had a single recursion. You had just this recursion that gave us that n+1 over n. But here in these higher rank cases, you have a recursive formula basically for each weight in each fundamental representation. So the number of recursions is equal to count the dimensions of each fundamental representation and sum them up. So for SP4, there's 7 recursions. And for G2, there's 21. And the recursive formulas get more complicated. So for SL2, we had K is -2 minus 1 over K. And this is one for just an random example for SP4. There's some more complicated recursive formula here. So the point that I'm trying to make is there's no way that you would guess this answer unless you had this guiding conjecture of Elias that said these coefficients that solve the recursive formula should be determined by the root system somehow. So there's some combinatorics hidden within these recursive formulas that say there's a product, there's some subsets of the positive roots that if I take this product analogous to the classic Weyl dimension formula, that solves these recursions, giving me the coefficients in my projectors. let's see. So actually, maybe I won't even go into that, but so I have a little tiny bit more about how this conjecture generalizes, but I don't know if I should just stop. Now we waited a little bit.
Yeah, if you, I mean, we have some time if you want to.
Okay,
yeah.
So I'll just say quickly, sort of maybe what's underlying this. So this is vague but conjectural, I think. Although some of the things are obviously theorems, just because they're not mine. So in general, if you have a representation of G, an integral weight, you can take X sub mu. This is the mu weight space of X. And I'm going to define this other thing, which is definitely thought of, but maybe less so than the mu weight space. And that's like a sort of E weight space. So if I have a dominant integral weight and just any subspace of X, I can compute what I'm calling cur sub lambda of W. And that's going to be the elements in W which are annihilated by a power of the E's. So this is in my Serre presentation. So the alphas are simple roots to one step past what the dominant weight is. So there's a theorem from a paper in the Annals of Math from 1967, 3 authors. I'm just going to say PR, this is the Prv formula, and it tells me what the dimension of Homs from V of lambda tensor X to V of lambda plus mu is. So I can compute this tensor product here by thinking about what the dimension of Homs are to various other representations. And I can do that just by computing the dimension of this cur lambda, which is how these E's act on the mu weight space of X. So I really love this formula, and it's probably the easiest way in practice for like just small representations that you're messing around with to figure out the decomposition of tensor products. So the consequence here would just be that you can actually decompose V of lambda tensor X into V of lambda plus mu's for various mu, as mu runs through the weight space of X. And the multiplicities are given by the dimensions of these subspaces, where you take a weight space and then you look at how the E's act on that weight space. And if you are a vector, if you're annihilated by a sufficiently high power of E, depending on this weight lambda, that contributes. So a quick example. So in SP4, this is like a picture of the representation V of omega 1. And I drew in here the action of the operators E. So if you have lambda is lambda 1 omega 1 plus lambda 2 omega 2, the kernel of lambda, so the way that E acts on x omega 1, so that's this vector, E always annihilates, both E's always annihilate this. So there's no condition. It's always equal to the full space. Now, if I look at the -1, 1 weight space, which is here, I need to do E2 always annihilates it. This always goes to 0. And then E1 squared will annihilate it. So I just need lambda 1 to be bigger than or equal to 1. Similarly, if I look at this weight space, E1 always annihilates it, but E2, it has to square to annihilate it. So I need lambda 2 to be bigger than or equal to 1. And then in this weight space, E2 always annihilates, but E1 I need to have square to annihilate, and so I need lambda 1 equal to 1. So for example, if I take V of a big multiple of the second fundamental weight and tensor it with the first fundamental, then I just get 2 summations. So this is, if you have a small enough or combinatorially understood sort of description of your representation X, this makes it pretty easy to understand how tensoring with this acts, at least just on the Grothendieck group of rep G. So the idea is that you have this V of omega, its mu weight space will have a filtration as lambda varies by these various kernels of raising operators. And if you have a basis adapted some way to this filtration, then there should be an association between each basis vector and some particular dominant weight, which depends on whether or not that basis vector appears in the kernel. So you let lambda vary, and you want to take the minimal, in some sense, lambda, such that this fixed basis vector, which is adapted with respect to this filtration, actually occurs in this subspace. And by the PRV theorem, it says that there's a map from this tensor product of the minimal thing with the fundamental weight to to this representation. And probably this map can be made canonical if, instead of working with representations, we work with representations with pinned highest weight vectors. Maybe it can't, but that's just a thought. And so what I'm trying to argue for is that, in some sense, these are our generating morphisms for the category fund. We want these maps to then be our choice of generators. It's overkill, but we kind of expect that this is the framework that we want to end up working. So for example, for SP4, so I just went over what the weight spaces were for these guys, and the diagrams that you get associated to this are these generating trivalent maps. And now let me just kind of end on this. So there's this recipe then for if I have any lambda, which gives me this vector in cur lambda acting on this weight space, then I can write lambda as the minimal lambda plus some extra junk. And I'm going to use this generating map to construct a map between tensor products v of lambda and v of lambda plus mu. And I'm calling these maps now, they're indexed by the I and the mu, that's telling me sort of which vector gave me that map. And the lambda and the omega, that's telling me where I came from. And maybe there's some extra data to keep track of. And then also, if I was doing diagrams and I had this map, I would just say flip that map upside down. But because I'm trying to formulate this in a diagrammatic free way, so this is, I'm going to say take the Hermitian adjoint, and you get this map going in the other way. So now I have an irreducible representation here. I have a map to this tensor product. I have this tensor product and a map to that irreducible representation, and I'm going to compose them. And my hope is that the one can prove without having the description of fund G by generators and relations, just using this general classic Lie theory, that the composition of these two maps is this product that occurs in Elias's class conjecture. So I give here finally sort of the description of what this subset of the positive roots are. So it has something to do with taking a minimal element such that it acts on that mu to be dominant, and then sort of taking a twist of that. So there's some subset of the positive roots that's giving me this coefficient in a Weyl dimension formula type way. And the dream is that if you could prove this without diagrams, you essentially use it to define some piece of your description of the web category that's your generators and relations for fund G, giving rise to this almost Sayre-like presentation of the category, where you only need to know about the root system and you get this presentation, and voila, it ends up being fund G. All right, so all of this last bit was highly conjectural, but I think it does sort of shed light that it should be possible to make sense of Elias's clasp conjecture without diagrams. It's not, it definitely, it should be something just about these maps between representations that is quite classical. Okay, so that's all I prepared. I'll just stop here and and say thank you for listening. Thanks for bearing with me.
Let's thank Elijah for that nice talk. And I'll stop the recording.